This is the second video in a two-part video series covering calculus in the polar coordinate system. This is based on section 7.4 out of the OpenStax Calculus book, volume 2. This section covers the area bounded by a polar curve as well as arc length for polar coordinate systems and tangent lines within polar coordinate systems. In this particular video, we're going to be taking a look at the arc length formulas and the equations for tangent lines in polar coordinates. In the previous video, we discussed how to find the area in a region bounded by a polar curve. You may recall that the formulas here in the center give the arc length for a curve in 2 dimensions. That is, on a plane curve, when it is written with respect to the variables x and y, we can find the length of the curve, L, when it goes from x equal a to x equal b by taking the derivative with respect to x, squaring it, adding 1, and then computing the square root of the sum. If instead we choose to do it with respect to the y variable, we will need to go from y equals c to y equal d, and then we will need to take the derivative of the equation with respect to y, square it, add 1, and then again take the square root of the sum. When we integrate these, we find the arc length. For a continuous function where the curve is not traced more than once, we can apply this formula to find the arc length formula for parametric curves. You'll see here at the bottom of the screen the formula for arc length with parametric curves. Recall that when we found this arc length formula for parametric curves, that it didn't matter whether we did the derivative initially with respect to x or with respect to y. Both led to the same formula with respect to the independent parameter t. That is, we need to take the derivative of the x equation with respect to t and square it. We take the derivative of the y equation with respect to t and square that too. After taking the sum of the two squares, we take the square root. Then we integrate along the two values that are given by t. Let's take a look now at what it looks like when we try to find arc length in a polar coordinate system. When we're looking at polar coordinates, remember that we define the equation in terms of the angle theta, which is considered the independent variable. That means that we generally give equations in terms of r or perhaps r squared. In this case, since theta is the independent variable and r is the dependent variable, we will give, instead of a and b values, alpha and beta values, which represent the small angle and the larger angle. In order to adapt the arc length formula for a polar curve, we'll need to use the equations that x equals r cosine of theta. Now, of course, r is itself a function of theta, which we can call f. This means that the equation for x is another equation based on theta, which represents r, times the cosine of theta. We can do the same thing for the y equation as well. Since y is equal to r sine of theta, and the radius r is also a function of theta, we can write y as f of theta times sine of theta. This is when we replace the parameter t, of course, by theta. If that is the case, then we can take the derivative of x with respect to theta by using the product rule. Remember that we will think of the radius function r as a function of theta. Thus, we have to have f prime of theta times cosine theta minus f of theta sine theta. You could also think of this as the derivative of r with respect to theta times cosine theta minus r sine theta. Similarly, for the derivative of y with respect to theta, we would get f prime of theta times sine theta plus f of theta cosine theta. Or if you prefer to write it in terms of r, you could think of it as r prime of theta with respect to theta times sine theta plus r cosine theta. You can think of it either way, but remember that when you find dx d theta and dy d theta, that you must consider r itself to be a function of theta. Let's go back to the original function for the arc length of a parametric equation, which you see in the first line on the left. We have said that this is equivalent to the equation on the right. How is this so? And how are we going to apply this equation that we see here? Based on the formulas we just had for dx d theta and dy d theta, we can now rewrite this equation here in terms of alpha and beta, which are theta angles, and dx d theta and dy d theta. Since dx d theta is the derivative of the r function with respect to theta times cosine theta minus r times sine theta, we can replace that here underneath the square root in the red color. Similarly, we can replace the expression for dy d theta with, again, the derivative of the r function with respect to theta times sine theta plus r times cosine theta. Once we have those there, we can, of course, square the binomial type objects. Don't forget that you should get at least 3 terms. It's not possible to square a binomial and end up with only 2 terms. You get the first term squared, which gives us the f prime of theta squared times cosine squared of theta. You get double the product of the outside and inside since the signs are the same, which leads to negative 2 f prime of theta times f of theta times cosine theta times sine theta. Again, keeping in mind that f is really the radius function as a function of theta. Then the last term squared will give us f of theta quantity squared times sine squared of theta. Similarly, if we square the expression that we had for dy d theta, we will get the expansion you see here in blue in the center of the screen. Once you have expanded the two, notice that the center terms of each expansion are in fact identical except opposite in sign. Because they're opposite in sign, of course, they cancel out. This leaves us with the first term squared and the last term squared of each of the expansions, which you see down here with the colors maintained to represent where it comes from. Now that we have simplified and gotten rid of the like terms, we can rearrange our terms. We want to rearrange things so that the derivative of the function f or r, quantity squared, is written first, and the function r of theta or f of theta was written at the back. If we group these like this, we'll be able to factor out those common factors in the next step. When we factor out the common factor of the derivative of the radius with respect to theta, quantity squared, we're left with cosine squared plus sine squared, which is one of our favorite Pythagorean identities, which we know is 1. Yay! It's gone. That simply gives us the derivative of the radius function with respect to theta, quantity squared. The second set of terms, we are able to factor out the common factor of the radius function itself, quantity squared. Remember that f here represents the radius function. In that case, we also are left with sine squared plus cosine squared. This, of course, also gives us 1, and we end up with the integral from angle alpha to angle beta of the square root of the derivative of the radius with respect to theta, quantity squared, plus the radius function itself, quantity squared. In other words, we can take this representation here in the pink color and rewrite it in terms of the radius with respect to theta. F prime of theta is, of course, dr d theta, and it is being squared. F of theta is the radius function itself, which here we've represented with simply r, but it could be written as r of theta. When you look at it this way, we often will rewrite it so that we have r squared written first and dr d theta written second, though of course it doesn't matter since addition is commutative. In polar coordinates then, the formula for arc length is the integral from angle alpha to angle beta of the square root of the radius function squared plus the derivative of the radius with respect to theta, the independent variable, quantity squared. However, I do need to caution you here. Finding the derivative of the radius function with respect to theta is not that simple. It's not a straightforward derivative because it requires the chain rule for derivatives. Remember that x is equal to r cosine theta, and that y is equal to r sine of theta, and that dx d theta involves the product rule, as does dy d theta. Since that is true, we can rewrite the derivative of x with respect to theta as r prime theta cosine theta minus r of theta sine theta. Be careful that you realize here that the notation r followed by parentheses of theta does not mean r times theta. It means r is a function and theta is its independent variable. Similarly, we can rewrite the derivative of y with respect to theta as r prime theta times sine theta plus r as a function of theta times cosine theta. Now, when you write it into a different form and you want to find dy dx, we can do something similar to what we did with parametric equations and the derivative there. To find dy dx, we will instead find dy d theta and divide it by dx d theta, just as we did with parametrics when we found dy dt and divided by dx dt. In this case, dy d theta gets replaced on top with the expression that we derived up here, and dx d theta gets replaced in the denominator with the expression you see derived up here. Let's take a look at example 1. It asks us to find the arc length of the polar curve r equal to e to the 3 times theta power when theta is between 0 and 2. Now theta is an angle which will be in radians unless otherwise specified. This means that theta goes between 0 radians to 2 radians. 0 radians is, of course, along the polar axis. 2 radians, however, since it's larger than 1.57, must be larger than pi over 2, but it is not as large as pi, 3.14. This must be somewhere just barely into quadrant 2, just past pi over 2. Let's now take a look at what this curve looks like between theta from 0 to 2 by graphing it in Desmos. Since we're in polar coordinates, we'll need to remember to switch to the circular target-shaped graph. Click on the wrench shape and then select the target-shaped graph under Grid. This will switch it now into a polar coordinate system. Now it expects to see r to the first power. Unfortunately, Desmos cannot yet handle powers greater than 1 for the radius r. Thus, if you have r squared, you must graph it in 2 pieces, the positive root and the negative root. We need to enter our equation now, which is r equal 3, or e to the 3 theta. Let's put that in now. R equals Euler's number e raised to the power 3 theta. Remember, to enter theta, you can simply type the word theta, T-H-E-T-A. Normally, the theta value for Desmos goes between 0 and 12 pi by default. We want it to go only up to 2. Just for fun, we can scroll in so we can see what the curve is looking like, though it does not appear to be doing anything too fancy other than simply starting out and then curling around. Although, if we keep going, we can see that it is in fact rotating all the way around. And indeed, it may in fact be a spiral. Let's go back in again and let's graph it only between 0 and 2. When we enter the 2 and hit return, it will graph the graph from theta equal to 0 to 2. If we scroll in just a little bit, we can see a little bit more of the curve. Now, it's hard for us to see everything that's on the graph. It may be that we need to scroll in more and more so that we can see how far it is going. Right about there is where it stops. You can see then that the graph is starting out in quadrant 1, curling around, crossing the 180-degree line that connects pi over 2 and 3 pi over 2, and heading off at an angle into quadrant 2. We want to know how long this curve is from the beginning out to where it stops. In order to do that, we'll need the formula. I've copied in the formula for arc length in a polar coordinate system, and up here you can see the graph that we produced through Desmos. Now let's compute the arc length for our equation, which is r equal to 3 theta in the power between the angle 0 and the angle 2 radians. That means that for our equation, alpha must be equal to 0 and beta must be equal to 2. Thus, we need to figure out what dr d theta is. Since alpha is 0 and beta is equal to 2, and we know what r is, e to the 3 theta, what's left to find is simply dr d theta. Remember that r is a function of theta itself, so you will often need chain rule. When you look at this, however, this r is a very simple equation. It is e raised to the 3 theta power. An exponential's derivative is the exponential itself times the derivative of the inside. There's your chain rule. The derivative of 3 theta is, of course, just 3. Thus, in this problem, we have a relatively simple dr d theta. We can set up the equation and the integral to find the arc length by integrating from 0 to 2 of the square root of the equation e to the 3 theta quantity squared plus the derivative function 3e to the 3 theta, that quantity squared, and integrate with respect to the independent variable theta. Remember that when you have a single base and 2 powers on it, that you need to multiply the powers. This will give me 6 theta for the first term. This gives e to the 6 theta plus, and now I need to remember that the 3 is inside parentheses, so it is being squared and will result in a constant of 9. And then the e is raised to both 3 theta and 2, which will result in e to the 6 theta as well, d theta. Now we need to integrate this. Our first step to the integration would be to factor out the common factor of e to the 6 theta. That leaves behind 1 plus 9. Or you could simply look at it and say that these two are like terms and 1 plus 9 would give you 10 of them. Because these are multiplied, we can split the radical between the two. This gives me the integral from 0 to 2 of the square root of e to the 6th theta times the square root of 10 d theta. Now, since e to the 6th theta can be taken the square root of, if we consider the square root to be the 1/2 power, that would lead finally to the integral from 0 to 2 of e to the 3 theta times the square root of 10 d theta. Remember again that the square root is the 1/2 power and half of 6 theta is 3 theta. Remember also that e is a positive constant, so it is not possible for the radicand to be a negative number. Since square root of 10 is simply a constant, it can go outside the integral. And this will leave us with the integral from 0 to 2 of e to the 3 theta d theta. At this point, a simple u substitution should bring us the result. Pause the video here, work out the details, and turn the video back on to compare your answer. You'll see that I pulled the square root of 10 outside, made a u substitution here, and also changed my limits of integration from theta values to u values. When I was done, I got the final answer of square root of 10 divided by 3 times e to the 6th minus 1. Let's take a calculator and see about how much that is. According to the calculator, that's roughly 424.2-ish units. Let's take a look back at our picture and see if we buy that. 424 sounds like a lot. However, if you look back at the unit circle here, notice that our curve had to get out to the circle of radius 400 before it got close. Now, how could it barely reach that circle yet be greater than 400? Simple, it curves. And because it curves, it has a length slightly longer than 400. This seems a very reasonable answer to me. Let's take a look at another problem. In example 2, we are asked to find the arc length of the polar curve given by r equals sine cubed of theta divided by 3, where theta goes between 0 radians and pi over 2 radians. Let's again go to Desmos to graph this so we can understand what we're trying to find the arc length of. If you still have the graph from the previous problem, you'll want to hit the house figure to return it to a more normal scale. Now we'll go ahead and put in the new equation. In this equation, we have r equals sine cubed of theta over 3. You can put in sine cubed, but I generally like to hedge my bets and go ahead and enter it as sine of theta divided by 3, and then close parentheses and do the cube separately. That closes the parentheses for theta divided by 3. The second set closes it for the sine. And then I can raise the entire thing to the 3rd power. Remember that ours is supposed to go from 0 to pi over 2. However, we can see from the picture that this could either be a limacon or a cardioid. Let's scroll in and see if we can see which one it might be. It looks a bit like it must be a limacon, since it looks like I have an inner loop developing. And a cardioid is more heart-shaped, as you can think of it as sort of the cardiac muscle, the heart, and it has a sharp cusp on it. This does not have a sharp cusp, but does indeed have an inner loop. This must be a limacon. When we're looking at this then, we need ours to go only from 0 to pi divided by 2. You can go ahead and type in pi in Desmos by simply typing pi, and then you can do divided by 2. Notice that this gives us a very small amount of the limacon, just this tiny little bit that you see here. Now let's go ahead and use our formula to compute the arc length of that small amount. In this particular problem, we know that our angle alpha is again 0 and our angle beta must be pi divided by 2. In this case, we're also told that r is equal to the sine function cubed of theta divided by 3. We need to find dr d theta. We will need chain rule here since we have both the sine function, a cubic function, and theta divided by 3. That gives us 3 layers we'll have to unpeel. The last thing that would be done is the cubic. Therefore, we undo it first. That's 3 sine squared of theta divided by 3. That simply undoes the third power. Now we multiply by the derivative of the sine function, since that's the second layer. Derivative of sine is cosine, but we leave the inside frozen. Now for the third layer, we need to take the derivative of theta divided by 3, which is of course simply 1/3. Notice that the 1/3 and the 3 that was obtained from the first outside layer will cancel, and this will simply result in sine squared of theta divided by 3 times cosine of theta divided by 3. This will give us dr d theta. However, to use the formula, you'll have to square that. Let's implement the formula now. When we implement the formula, we need to square r. If you take something that's cubed and you square it, it means it's a cube squared, and that means it's being raised to the 6th power. Remember to multiply powers when you are having one base and 2 powers. Arc length then will be the integral from 0 to pi divided by 2, from alpha to beta, of the square root of sine to the 6th power of theta divided by 3, plus, now we need to square dr d theta. Since this consists of 2 factors, sine squared and cosine, sine squared squared becomes sine to the 4th of theta divided by 3, and cosine becomes cosine squared, also of theta divided by 3. All of that represents the radicand. Then we will integrate with respect to theta, and we need the differential d theta to do that. Now we look at these two and we try to find a common factor if possible. We do have one. It's the sine to the 4th power of theta divided by 3. Let's factor that out now. After factoring out the common factor, that will leave me with 2 factors. The common factor, sine to the 4th of theta over 3, times what was left behind. And when I pull 4 out of the 6 that were originally there, I'll end up with sine squared of theta divided by 3. When I pull the sine to the 4th off the second term, I have cosine squared of theta divided by 3 left behind. Notice that in this case, the second factor, both trig functions have an argument of theta divided by 3. Because they're identical arguments and they're sine squared plus cosine squared, I can use the Pythagorean theorem and say that this is represented, of course, by 1. That lets me simplify things a great deal. This then becomes the integral from 0 to pi over 2 of sine to the 4th power of theta over 3, integrated with respect to theta. Now we need to take the square root of sine to the 4th. The square root of sine to the 4th would be sine squared. Normally, when you take a square root, you need absolute values to force it to be positive. However, something that is squared must be positive, so I can drop the absolute values. Now I've got sine squared of theta over 3 as the integrand. In order to integrate sine squared, we learned at the beginning of the semester when we were studying trig integrals that we need to substitute the double angle formula, or you can call it the half angle, depending on which way you want to go. In order to replace sine squared, since sine is an odd function, This is the one that has the minus in it. This becomes 1 minus the cosine of double whatever the argument was originally. Since my argument was originally theta over 3, the new argument is 2 theta over 3. And I'm going to integrate again with respect to theta. I can factor out the constant factor of 1/2 and split the integral into two separate integrals. This becomes the integral from 0 to pi over 2 of 1/2 d theta minus 1/2 the integral from 0 to pi over 2 of cosine of 2 theta divided by 3 d theta. Again, we're going to need a simple u substitution in order to complete the integration on the second integral. The first integral, of course, simply gives us 1/2 theta, which will need to be evaluated between 0 and pi over 2. For the second one, we'll make a substitution that u is 2 theta divided by 3, which results in du being 2/3 d theta. If we divide by the fraction 2/3, which is the same as multiplying by the reciprocal 3/2, we get that 3/2 du is equal to d theta. Let's also switch the limits of integration on the second one so we don't need to return to theta. When theta is equal to 0, the u value, since it is 2 times theta over 3, is also 0. When theta is equal to pi over 2, however, u, which is 2 theta over 3, becomes 2 over 3 times pi over 2. That results in pi over 3 for the second limit of integration. This will let me rewrite the second integral then as minus 1/2 the integral with the new limits of integration of 0 to pi over 3 of the cosine of u times 2/3 or 3/2 du. This is because we are replacing d theta with 3/2 du. Note that the 3/2 is simply a constant and can come out to the front. In the next step, I'll go ahead and plug in the limits of integration into the first term, leaving the 1/2 to be done after. This gives me pi over 2 minus 0, which results in pi divided by 4. For the second, I can pull the 3/2 to the front to join the 1/2, and that will give me minus 3 divided by 4. The antiderivative to cosine is sine, and then I need to evaluate the sine of u between 0 and pi over 3. For the next step, what I want to do is plug in the limits of integration in place of the variable u. I will leave the minus 3/4 until after that is done. This gives me sine of pi divided by 3 minus the sine of 0. Plugging in these values then gives me the following. Since the sine of pi over 3 is the square root of 3 over 2, and the sine of 0 is 0, this results then in pi over 4, again from the first term, minus 3 over 4 times the square root of 3 over 2. This gives me a final result of pi over 4 minus 3 square roots of 3 divided by 8. Let's check the calculator and see about how long that is. According to the calculator, this is roughly 0.136 units long. In other words, incredibly small. Let's take a look back at our picture and see if we buy that. In our picture, which you can see here, you'll notice that it is not very far outside of this inner circle. How big is that inner circle? You'll notice here that there is a notation on this darker one that it is 0.5, which makes this one here roughly 0.1. It is further than that circle, so it is greater than 0.1, and it curves a bit, which makes it a bit longer. So that makes sense that it would be roughly 0.136 units long. Before we start looking at tangent lines in the polar coordinate system, let's take a moment to remind ourselves what a tangent line in the parametric coordinate system is, since it is very similar. Once we've reminded ourselves of how to compute a tangent line in a parametric system, then we will look at how to find the tangent lines in the polar coordinate system. Let's remind ourselves with this problem here in example 3. In the curve that you see here, this is called a prolate cycloid. In other words, it kind of comes in, makes a loop, and then goes off again. It's crossing itself at a point that occurs on the x-axis. We want to find the equations of the tangent lines at that point where it touches and crosses the x-axis and crosses itself. There are two. One comes from this direction. As you're tracing around, you'll see that there is one right there going in that direction. There's another, though, if you're coming from the other direction and you go up this way, there's another tangent line at exactly the same point. It depends upon the orientation as to which tangent line would be the most appropriate for your situation. How do we find the equation of a tangent line in a parametric system? The most important thing to remember is that whether you're talking about a rectangular or Cartesian coordinate system, or a parametric coordinate system, or a polar coordinate system, that the slope of the tangent line is still given by dy dx. In other words, we still need to find dy dx. How do we find dy dx in a parametric system? For the parametric, remember that we take an abuse of notation, dy dt divided by dx dt, to get dy dx. Similarly, in a polar coordinate system, we'll do dy d theta divided by dx d theta. Recall, however, that because both x and y depend on both theta and r, which also depends on theta, that both of those will require the product rule. This is different from a parametric system. In that sense, the polar system is more complicated because dy d theta is more complicated generally than dy dt, and dx d theta is more complicated generally than dx dt. Let's finish this problem and then apply what we do here to the polar coordinate system. I'm going to go ahead and find dy dt and dx dt. I originally had theta here instead of t, so if you've already copied down the problem, you want to fix that and make this a 2t instead. Dy dt then, the derivative of y with respect to t, would be given by 2 minus, and then for the second part, the derivative of sine is simply cosine. Pi is simply a constant, which is the coefficient, and simply follows along. Thus, dy dt is 2 minus pi cosine t. For dx dt, we get the following. Since 2 is a constant and it is a term by itself, its derivative goes to 0. This will give us the derivative of negative pi cosine t. Pi is again a constant with a negative attached, but the derivative of cosine is negative sine, which gives us a double negative. This then results in pi sine of t. Now, the next thing we need to figure out is, at what point is it that we want to figure out the tangent lines? In other words, we need to know what is the t value when it crosses itself here on the x-axis. There are a couple of different ways of finding it, but one of the simplest is to realize that when you're on the x-axis, the value of y must be 0. So we can use that to find t. On the x-axis, y is 0. Now we'll take that information and set 2t minus pi sine t equal to 0. 2t minus pi sine of t has to equal 0. Now, how can we find the solution to that equation? It's not possible to isolate both t's at the same time. One of the t's is inside of the trig function sine, and the other is not. If you're to get your hands on the one inside the trig function, you would have to apply the arcsine function, but that will bury the one that was not inside of a trig function. It's not possible to solve for these t's at the same time. Given that, the next best thing we can do is solve for the t that's not inside the trig function. That means that I can now rewrite this as 2t equal to pi sine of t. Then I can divide both sides by 2 and get that t is equal to pi over 2 times the sine of t. Now, how can I make this true? You could, of course, put these onto a parametric graph and look to see where they cross the t-axis, or, in a different sense, look to see where the two sides are equivalent to one another. However, a little bit of thinking and a little bit of logic will tell you that when t is itself pi over 2, then the sine of pi over 2 is 1, and that would give me pi over 2 equal to pi over 2. That seems to indicate that I should be looking possibly at multiples of pi over 2. Let's take a look at some of those now. For example, when t is equal to pi over 2, then pi over 2 is equal to pi over 2 times the sine of pi over 2, since the sine of pi over 2 is 1. What would happen if I used, for example, negative pi over 2 or 0? If I were to use 0 for the value of t, then I would want to know, is 0 equal to pi over 2 times the sine of 0? The sine of 0 is 0, and 0 times pi over 2 is, of course, 0, so this one also works. What about negative pi over 2? Let's take a look at negative pi over 2. When t is equal to negative pi over 2, then negative pi over 2 to replace the t, is that equal to pi over 2 times the sine of negative pi over 2? Remember that negative pi over 2 is also in the same place as 3 pi over 2, which means, of course, that its value is negative 1. That would say then that negative pi over 2 equals negative pi over 2, so that negative pi over 2 is another solution. What about 3 pi over 2? Would 3 pi over 2 work? When t equals 3 pi over 2, I'm asking, is 3 pi over 2 equal to pi over 2 times the sine of 3 pi over 2? This time I get a no. The sine of 3 pi over 2 is equal to negative 1, which gives me negative pi over 2 on the right, but that is not equal to 3 pi over 2 on the left. If you continue in a similar fashion, you'll discover that we already have the only three solutions: pi over 2, negative pi over 2, and 0. To illustrate this idea, I've used Desmos to graph y equal to x and y equal to pi over 2 sine of x. Since Desmos typically thinks of t as a parameter, I needed to substitute out t and replace it with x. You'll see on the graph that there are only 3 places where these two curves intersect, and that there can be no others, since this graph extends up forever and down forever and will never again cross the oscillating sine function. Let's return now to our problem. When we were last looking at the problem, we had to find 3 values where those were equal. We did find the 3 values where they were equal. The question is, of the 3 values that we found, which is the one that corresponds to this point here on the x-axis? We have 3 possible values for where that could occur, but note, of course, that we've got this point over here on the loop that is also on the x-axis. We don't know yet which of the t values corresponds to the place where it crosses itself, one when moving in this direction and one when moving in that direction. Let's now consider which one it could be by taking a look at the function values and comparing them to our possible t values. Here's what the equation looks like. Now that we have this equation and we have 3 possible t values, which one would it possibly be? We have negative pi over 2 as a possibility, 0 as a possibility, and pi over 2 as a possibility. We know that all 3 of these will cause the y-coordinate to be 0. However, on our graph, notice that the x-coordinate is clearly off to the right between quadrants 1 and 4. That means the x-coordinate here should be positive, whereas the x-coordinate here would be negative. Now when we look at this 3 values and we plug them into the x equation, I get that the cosine of negative pi over 2, which is 0, gives me an x value of simply 2. Likewise, since cosine of pi over 2 is also 0, this one also gives me an x value of positive 2. That seems to mean that both pi over 2 and negative pi over 2 are the points that result on the positive x-axis. Let's check and be sure. If I plug in 0 for t, the cosine of 0 is 1. 2 minus pi is about a negative 1.14, which is negative, which must mean that it corresponds to the point out here on the left side. Thus, the 2 t values we need are pi over 2 and negative pi over 2. Now we need to finish the problem. Our job was to find the derivative and the slope of the tangent line at that point. The slope of the tangent line is given by dy dx, and for us, the angle is going to be either negative pi over 2 or positive pi over 2. Now we need to go ahead and find the value of dy dx. You will recall that at the very beginning, we said dy dx is the ratio of dy dt divided by dx dt, and that dy dt is 2 minus pi cosine t, and dx dt is pi sine of t. Therefore, we must have dy dx to be 2 minus pi cosine t divided by pi sine of t. Finally, writing that equation for dy dx and replacing t with negative pi over 2 leads to the derivative being 2 divided by negative pi. Replacing t with pi over 2 leads to the derivative being 2 over pi. Now that we have the slope of the tangent line at the 2 points, we need to find the points. Since of course we are on the x-axis, we know the y-coordinate must be 0, but what about the x? And to find this, we need to find the value of x at t equal to negative pi over 2 and x at t equal to pi over 2. If I plug that into the x equation, which you see here in the upper left, then we get that x is equal to 2 minus pi cosine of negative pi over 2, which of course is simply 2. Similarly, when we plug in t equal to pi over 2, we also come up with 2. We can write the equation in point slope form then by y minus 0 equal to, for the one on the left, negative 2 divided by pi times x minus 2. And for the one on the right, y minus 0 equal to 2 divided by pi times x minus 2. If you prefer slope-intercept form, you can, of course, drop the minus zeros and distribute the slope over the parentheses. Now let's move on and take a look at the polar coordinate system and see how we can apply what we've remembered about parametric systems to the polar system. In example 4, we're to find the equation of the tangent line to the polar curve given by r equals 2 cosine theta at the point theta equals pi divided by 3. Now, of course, theta equal to pi divided by 3 is not truly a point. It's only half the point. In order to find the rest of the point, we would need to plug that into the radius function. Remember, however, that unlike the rectangular system, in the polar system, the independent variable theta is listed second, and the dependent variable r is listed first. The other coordinates of the point would be found by replacing theta in the equation for r with pi divided by 3. Since the cosine of pi divided by 3 is 1/2, then this tells us that the radius at that point must be 1. That gives us the coordinates of the point where we're to find the tangent line. However, we need the slope at that point. Remember that when you're looking for slope, you are still looking for dy dx, but you're looking for it when theta is equal to pi over 3, and of course, when r is also equal to 1. Now let's take a look at what the formulas are and remember how to apply this to the polar coordinate system. At the beginning of this video, we went through a long derivation of why this formula is correct, but at this point, we'll simply cut to the chase. Recall, however, that because x and y are functions of more than just theta, in other words, x being r cosine theta, means that since r is a function of theta and cosine is a function of theta, that we have to use the product rule. That's why we get two terms in the numerator and denominator when we try to compute dy dx in the polar coordinate system. We use the same abusive notation that we did in the parametric system, except that we replace dt with d theta. The differential here must match the independent variable, and in the parametric system it is the variable t, and in the polar system it is the variable theta. Now for the rest of it, we simply need to compute these pieces and plug them into the equation for dy dx. Then we'll plug in that theta is pi over 3, and we can also use our information that at the same point we're interested in, the radius is in fact 1. This may simplify a little bit of our work when we are needed to find r as a function of theta. We won't need to go back to the original equation. We can use the value we've already found. Now let's take a look at applying the formula. To apply the formula, I will need to have dr d theta. To find dr d theta, then, I simply take the equations and find the derivative with respect to theta. In this case, I get negative 2 sine of theta. Now I need to plug that into the formula for dy dx. That gives me the following. dy dx is equal to dr d theta, which is negative 2 sine of theta times sine theta. This sine theta and this sine theta are not the same. One came from the derivative of r with respect to theta. The other came from the formula itself as a result of the product rule. In the second term of the numerator, we need the value of r itself. We can simply write plus r and then cosine of theta. In the denominator, we'll start with dr d theta again, which is, of course, negative 2 sine of theta, now multiplied by cosine theta. The cosine theta is part of the formula and will never change. The second term is r sine of theta. Now notice that the numerator has a plus in between and the denominator has a minus. That is because x is dependent on cosine and the derivative of cosine is negative sine. That's what gives you the negative in the middle. And the next step, we simply need to evaluate this at our point 1 comma pi over 3. So then we'll compute dy dx at the point 1 pi over 3. That means that wherever I have theta, I will replace it with pi divided by 3. Notice that I have two signs, which of course gives me sine squared. For the second term in the numerator, I can replace r with its value at that point of 1. Cosine is, of course, going to have to apply to pi over 3. In the denominator, they're not the same, so I have to leave them separate. This is sine of pi over 3 times cosine of pi over 3 times a negative 2 minus r, which is 1, times again the sine of pi over 3. You may instead want to figure out to the side what the sine of pi over 3 and the cosine of pi over 3 are and plug those values into the formula instead. Let me show you what I mean. You could go to the side and compute that the sine of pi divided by 3 is the square root of 3 over 2, and that cosine of pi over 3 is equal to 1/2. Then when you write out the derivative formula, you could replace the sine of pi over 3 instead with the square root of 3 over 2. Since the first one is squared, it will be in parentheses squared. The second one, we would replace cosine of pi over 3 with 1/2, which of course would get multiplied by the radius, which ours is 1. In the denominator then, I would have negative 2 times the sine of pi over 3, which is square root of 3 over 2, times the cosine of pi over 3, which is 1/2. The second term in the denominator will be subtracted. Our radius is 1, and sine of pi over 3 is, of course, square root of 3 divided by 2. That might simplify some of your writing and some of your work. When I square the square root of 3 over 2, I end up with 3 over 4. If I then simplify that with the negative 2 on the outside, I should end up with negative 3 over 2, since 2 divided by 4 is 1/2. Added to that, I have 1/2 in the numerator. In the denominator, I could cancel one of the 2's with the 2 in the denominator. That still leaves a 2 in the denominator and a negative. That leaves behind negative square root of 3 over 2 minus another square root of 3 over 2. You can combine your like terms in the numerator to get negative 3/2 plus 1/2 is negative 2/2 or negative 1. In the denominator, negative root 3 divided by 2 minus another root 3 divided by 2 is negative 2 root 3 divided by 2, which is simply negative root 3. The double negatives cancel, and I get 1 divided by the square root of 3. You may have forgotten what the point of all this was, so let's go back to the problem and see. Oh yeah, we're supposed to find the equation of the tangent line to the polar curve at this point, 1 pi over 3. And what I found was the slope. All that remains to be done is to put it into slope-intercept form or point-slope form. In point-slope form, remember that you need to use the x and the y values, since that is the form that we need to have it in. To find the x and y values, you will have to come back up here to where r is and also use the information about what theta is to compute x and y. Let's take a look at that now. Recall that r is 2 cosine theta. Recall that the formula for x can be given by x equals r cosine theta. That leads us to then write that in this case, if I want to find the value, remember at this point r is 1 and the cosine of pi over 3 we found is 1/2. That gives me 1 times 1/2, which is equal to 1/2. To find the y value, similarly, you will multiply r times the sine of theta. R is 1, and again, recall that we found the sine of pi over 3 to be square root of 3 over 2. That results in square root of 3 over 2 for the y value. Putting that together with what we found for the slope, I can put it into slope-intercept form or point-slope form. First, I would start with point-slope. Y minus square root of 3 divided by 2 equals the slope, 1 divided by the square root of 3, times x minus 1/2. If I wanted slope-intercept, I would distribute the 1 over the square root of 3 and add the square root of 3 over 2 to both sides of the equation. Let's take a look now at example 5. In example 5, we're asked to find the equation of the tangent line to the polar curve given by 4 minus 3 sine theta at the point where theta is equal to pi. Of course, theta equal pi is again not a point. It's only half the point. Let's start by computing the point. When we're looking at this particular one, in order to find the rest of the point, we need to plug in theta equal to pi into the equation for r. This gives me 4 minus 3 sine of pi. The sine of pi, however, is 0. That means that the radius is simply 4. That will let me write the ordered pair as 4, pi. To locate this point, of course, you would go in the pi direction, which would be off in the opposite direction to the polar axis, and stop on the 4th radial circle. That would be this point here. Now we need to find what the equation of the tangent line is to the polar curve at that particular point. What we'll need to start with then is the equation for the derivative of y with respect to x. dy dx is going to be given by dy d theta divided by dx d theta. Now, you can either memorize the formula or you can simply apply the product rule every time. I'll confess, I don't generally memorize the formula. The ones I know, because I use them so often, are that the y value is r sine theta and the x value is r cosine theta. Now I can simply do the product rule on those. R is also a function of theta, so that's why product rule is required. That will give me dr d theta times sine theta plus the derivative of sine is cosine, so I get r cosine theta. In the denominator, the derivative of the first factor is dr d theta, and I leave the second factor as is cosine theta. Then I take the derivative of the second factor cosine, which is negative sine, and multiply by the first factor, which is r, minus r sine theta. Again, this is not a difficult formula to memorize, but it is something to memorize. Personally, I'd rather memorize these much simpler ones and simply remember that I have to use the product rule in order to derive it. In order to use this formula now, I need dr d theta, and I will need to know what the sine and cosine are at the value of pi. Let's go find those values now. If I'm looking for dr d theta, I would come up with the following. Dr d theta would be equal to, based on the formula here, the derivative of 4 would be 0, derivative of sine is cosine, so I get negative 3 cosine of theta. Now I want to compute the value of sine and cosine at my angle, which is pi. Then I'll plug in the values into the formula. This will give me the sine of pi, which of course is 0, and the cosine of pi, which of course is -1. Now I'm going to plug these into my formula. This leads to the following. dr d theta is -3 times the cosine of theta, but my theta is pi, and the cosine of pi is -1, so I can write -1. The -3 times -1 represents dr d theta. Then I multiply by sine of theta, which is 0. So the whole first thing drops out. Now let's look at the second term. This will be r, which I found previously to be 4, times the cosine of theta, which I found down here to be -1. This is divided by dr d theta, which I found in the numerator to be -3 times -1, or +3, times the cosine of theta, which of course I found to be -1. Then I have a subtraction in the formula because of the derivative of cosine. The r value I found previously to be 4. Then I multiply by the sine of theta, which is, oh yeah, it's 0. That means the second term in the denominator drops out. What does this leave behind? This leaves behind the derivative value at that particular point of 4 pi as being -4 divided by -3, which is a +4/3. Let's look back at the picture and see if we buy that. If I were to superimpose a rectangular coordinate system, this tangent line here does look like it could have a slope of +4/3. It's clearly positive, and it looks steeper than the 45-degree angle line. Let's now put it into point slope form to finish the problem. In order to do this, we need the y value and the x value, but we've already computed the sine and the cosine and the radius. Then I get that y is equal to the r value, which is 4, times sine of theta, which is 0, so that the y value is 0. The x value is given by r, which is 4, times the cosine of pi, which is -1. That gives me an x value of -4. Again, looking at the picture, it's clear that's where I would be in a rectangular system, at -4, 0. Using those points, I can now put it into point slope form, but I can ignore the -0 since it won't change the left. And I can write that this is y equals 4/3 times the quantity x minus a -4. Of course, a double negative would give me a plus, and if you really want to go the extra mile, you could go ahead and finish it out and put it into slope-intercept form. This would be 4/3 x plus 16/3. Let's take a look at one more example. In example 6, we're to find the equation of the tangent line to the polar curve at the pole. Remember, the pole coincides with the origin. When you're at the pole, the radius is 0. What angles might put us there? So again, we need to remember that at the pole, the radius is 0. What is theta? Now, to find that, let's see what we can get out of the equation 2 cosine of 3 theta equals 0. If I'm restricting my attention to the angles between 0 and 2 pi, I know that if I divided both sides by 2, I would still have an equivalent equation. And this would tell me that the cosine of 3 theta must be 0. Cosine, of course, gives me 0 when it's at either pi over 2 or 3 pi over 2. That means that 3 theta must be equal to pi over 2 plus any pi over 2 integer multiple. N could be any integer, positive or negative, or 0, and I would end up with some pi multiple of pi over 2 where the cosine would be 0. In order to complete this problem, the simplest thing to do, oops, I think I wrote pi over 2 instead of pi. This should be a pi multiple of pi over 2. In order to make it simpler, what we need to do is get a common denominator. This becomes then pi over 2 plus 2 pi n over 2, which is easier written as pi plus 2 pi n all divided by 2. In this case, I now need to divide both sides by 3. I can also think of multiplying by 1/3. That will give me an equivalent equation. So theta must be equal to pi plus 2 pi n divided by 6. Let's think about what the different values for this could be, and how many different equations we could have for a tangent line to a polar curve at the pole. There are many different angles here that would result in being at the pole. We'll first let n be 0, and then we'll go off to the right and to the left. If I use these values, this should take me around at least one time. If n equals 0, I of course just get the angle pi over 6. When n equals 1, I add on another 2 pi over 6, which gives me 3 pi over 6, which of course reduces to pi over 2. When n equals 2, I'll add on 4 pi over 6, which brings me to 5 pi over 6. If I were to add on another one, I would come up with the next value, which would be 7 pi over 6, and then, of course, 9 pi over 6, and then 11 pi over 6. This would bring me around to 12 pi over 6, which is also 2 pi. You could also go backwards if you prefer to do a 2 pi circle in that direction as well. Now let's take a look at what the graph looks like so that we can interpret what this means. Bringing in Desmos again, I'll clear out what was here previously on the rectangular system, click on the wrench and the circular graph so that I can return to polar coordinates, and then enter my equation 2 cosine of 3 theta. As you no doubt anticipated, we do have a rose with 3 petals. Since 3 is an odd number, we get the precise number that corresponds to the coefficient of the argument to the trig function. The length of each petal, of course, is 2, which corresponds to the coefficient of the outer trig function, but not the argument. Now what we need to know is, when does it reach the pole? Multiple times. Let's start here on the positive polar axis and trace it in the counterclockwise direction. Here I hit the pole the first time, probably at pi over 6. Then it loops around in quadrant 3 and hits the pole at pi over 2. Then it loops around in quadrant 2 and it hits the pole again, and this must be at, what was the next one we found? That was at 5 pi over 6. Our next one coming around, after we hit here at 5 pi over 6, it's going to come back around to the beginning. In other words, we have probably traced this out by the time we get back around over here. That means that it is traced twice when we go from 0 to pi, so we don't need to go from 0 to 2 pi. We'll simply look at the different ones at the 3 different angles, pi over 6 and pi over 2 and 5 pi over 6. Let's take a look now at what we have. Here are the three angles that we found where it hits the pole in one trace of the three-leaf rows. What we need to do now is find a formula for the derivative dy dx. This time we will not plug in the particular angle since we need to have it at three different angles, but instead we'll come up with a formula which we can then plug in the angles for later. Our 3 points that we're going to consider will be 0 pi over 6, then 0 pi over 2, and again 0 5 pi over 6. I know what you're saying and what you're thinking. When you're looking at the graph, you're used to thinking in terms of rectangular systems, and you're saying, but that's the same point. It is the same point at a different place along the path. That means it's not the same point because you got there at a different point in time. In other words, it can't be considered to be the same. The tangent lines will change because the angle at which you approach the pole changes with the angle. That will give 3 distinct tangent lines. Let's now take a look at what those would be. First, we need to compute the derivative of y with respect to x. Pause the video here, do the computations on your own, then turn it back on and compare your answer. Let's check it out. Did you get this expression here? Hopefully, if you did, you then realized that you could do some simplification. I left it here so that you could see what happened. Notice that when I took the derivative of r with respect to theta, I had to incorporate chain rule because the argument to the sine function was 3 theta. That gave me -6 sine of 3 theta. When I plugged it in, you also need to remember that at the pole, the radius is 0, which causes both of the second terms to drop out. This gives us dr d theta times sine theta in the numerator and dr d theta times cosine of theta in the denominator. But that means that it doesn't actually depend on dr d theta at all, since that becomes a common factor and can, of course, then be canceled out itself. That means that my final resulting formula for dy dx is simply sine theta divided by cosine of theta. Now let's take that and use the 3 points that you see here and compute what our tangent lines would be coming from the 3 different angles. We'll start with 0 pi over 6. When I'm at the point 0 pi over 6, then I know that my dy dx must be given by sine theta over cosine theta, which means that I have sine of pi over 6 divided by cosine of pi over 6. The sine of pi over 6 is 1/2, and the cosine is the square root of 3 over 2. The 2's cancel, and I get 1 over the square root of 3. This allows me to then think about this and to write the equation once I've found the x and the y value. But remember, I'm at the pole. And when I'm at the pole, if we come back up here, at the pole, that means that we must have the x and y coordinates being 0, 0, since the pole and the origin coincide. That means that my x and y are both 0. Well, then how can I put it into point-slope form of the line? Well, it's simple. Y minus 0 equals 1 over the square root of 3 times x minus 0 simply gives me the equation y equals 1 divided by the square root of 3 times x. What would happen if I used the second point? The second point was 0 pi over 2. This was after it had made half of the first loop, the full second loop, and was coming back around in order to make the third. Let's do 0 pi over 2 now. If the point is 0 pi over 2, then my derivative formula for dy dx becomes the sine of pi over 2 divided by the cosine of pi over 2. I was expecting to see this. I know cosine of pi over 2 is 0, but don't freak out. This just means it's undefined. If it's undefined, it's a vertical line. Well, let's see what it actually looks like when we pull the graph back in. Remember that what's happening is after I started here, I came down. Now I'm approaching at the angle of pi over 2, which is this direction. Do you see that as it comes around from quadrant 3, this tangent line goes vertical? What is that tangent line? Well, it's at the origin, so it's just the y-axis itself. That must be x equals 0. So that one becomes sort of a simple one to write down, x equals 0. Now let's look at our third point. Our third point that we had where it hits the pole is 0, 5 pi over 6. This is as it's coming in for the final bit of the second half of the first loop it started making. This is 0, 5 pi over 6. For that particular point at the pole, the derivative dy dx becomes the sine of 5 pi over 6 divided by the cosine of 5 pi over 6. Well, the sine of 5 pi over 6 is a positive 1/2, but the cosine is going to be a negative square root of 3 over 2. The 2's cancel, and I get a negative 1 over the square root of 3. Using a similar idea to what I did in the first, I know that this will lead to a simplified equation for the tangent line of y equal negative 1 over the square root of 3 times x. Again, let's go back to the picture to make sure that this makes sense to you. This last one is coming in from quadrant 2 as it comes around and is headed towards quadrant 4. That's where the 5 pi over 6 line is, right here. As it comes in, do you see that this tangent line is sloping downhill? That's why the slope is negative. I hope that this makes sense to you and that you now understand how to find both the arc length and the tangent line in the polar coordinate system. In the next video, we'll be taking a look at how to think about conic sections in the polar coordinate system. Conic sections are one of the reasons that we study the polar coordinate system. It is much simpler to write the equation of an ellipse, a circle, a hyperbola, and a parabola in a polar coordinate system than it is in the rectangular coordinate system. This is the end of this video.